is because this is really important. If you know this one conversion, you can usually, now we know, right? So if it's 1/4 of an inch, we'll take this divided by 4, take this divided by half for 1/2 inch, so forth. That's one of your best conversions alone. 25.4 millimeters. 1 inch in the English system. Let's go to our book, page 977. It gives you a good, a couple of good measurements and conversion tables there on the top. You're going to see some terminology that you've never seen before. So for example, let's look at flow rate. Okay? So underneath flow rate, what it states take a minute and go through this just so that we understand how to use this conversion. Okay? Check the camera, make sure you can see. I'm going to zoom in a little bit. Okay. So we're under flow rate. Okay? So say we're at cubic feet per hour. Now in the welding terminology, this is a lot of what we're going to see is CFH. The way that it's wrote here in the book is feet cubed per hour. Okay? So if we're reading a welding procedure and it says that your shielding gas should be 20 cubic feet per hour, 20 CFH, okay? So from 20 CFH, we need to make sure that we convert that to liters per minute. So to convert from cubic feet per hour to liters per minute, you multiply by 0.4 0.4719. Okay? You can do it in a calculator or fairly quick. Okay, so we got 9. So then we got 0. Sorry. Yeah. Add another 0. Sorry. Okay, start over again. 9 times 0, 0. 9 times 2 is 18. I'm going to add a 0 to start with. 1 times 0, 0. 1 times 2, 2. Now we're 3 spots over. 7. 1, 2. 14. So now we're going to go 1, 2, 3 zeros, 4, 0, 8. 0, 8, 3, 4, 9. 4 decimal places. 1, 2, 3, 4. 9.438. So let's just double check it. We should be fairly good. Times 0.4719, 9.438. Now just a quick check real quick. 20 times 0.5 is almost 10, correct? Say we don't have a calculator out there. 20 times 0.5 is almost 10. We're just below it. I'm going to assume my math is pretty close there, okay? If not, I would have ended up like 8, and we know that that might be a little bit off. Then I'm going to redo it again just to double check and make sure. All right? So now we have 20 cubic feet per hour equal to 9.438 liters per minute, correct? Correct. Okay. Let's look at pascals. There's some different terminology in there that you're not familiar with yet. Look down under pressure. 1 psi to convert it to a kilopascal, kPa. 1 pounds per square inch is equal to 6.895 kPa. So kilo is 1,000, right? Kilo is 1,000. So if we say another way to make it simple, so we got rid of the killing, we now have 1 psi is equal to 6,895 pascals. Okay, so this is a metric form of, one metric form of pressure, pounds per square inch. Part of the reason they abbreviate is because the numbers get larger. Okay? Let's look underneath at a mega pascal. That is equal to 0.0006895, I believe. Is it 3? 2, sorry. So Kelly's got 1, 2, 3, so 1,000. Okay. Mega, 1, 2, 3, 4, 5, 6. 1 million. Okay. 6 zeros. And that matters when we start dealing with, say 30, say we take a stainless steel. What's the tensile strength of stainless steel? Let's give it a fairly just odd number, 120,000 psi. And if we converted that to just normal pascals, 6,895, we would have this tremendous number of 1 and 2, so we're going to be, we're going to be somewhere around just off the top of my head, we got 3, 3, 6 times 12 is 6, 72. So we're going to be about 72 billion pascals. Okay? Now we may be able to take that and convert it in. Let's do the conversion here real quick of what they say on my calculator. So to take it from psi to megapascals, so we're at 120,000 times 0.006895 is equal to, well, I was off. Of course, I didn't add these, I just did 6 times 12. So we are at 827.4. Okay? Sorry, I got a little happy with the zeros. Hopefully you can still see that. Okay. 827,400,000, so forth. So now we're going to move 1, 2, 3, 4, 5, 6. 827.4 megapascals. Okay? So we talk about doing those conversions. Just look at this table. Do a couple of them to keep in mind. So forth as far as measurements. Remember 1 inch is equal to 25.4. Okay? And that's on linear length, not area. Okay, let's keep moving on. Excuse me. Application of SI to drawings, okay? Okay, we're going to move on to methods of dimensioning. Locations indicated by the arrowhead like we showed. However, when the area is too small, you may see something very similar to this. Outside measurement, inside measurement here. What you just need to follow the arrows or the leaders to make sure to show you the exact dimensions, okay? So here's more examples of dimensioning. Trying to see where we are in the book. It looks like we're on page 980. However, I want you to look back on page 978. There are multiples and submultiples of base 10. They explain the prefixes for the metric system and so forth. Quite important to know as well. Okay. Now let's go to page 980, chapter 29. We're back under methods of dimensioning, and we're going to look at diameters and radius. Okay. Okay. So real quick, we have a 1-inch diameter. It can be dimensioned on the internal. However, if there are other things within this circle, sometimes you will see an outside dimension of 1 inch. Okay, a lot of times on a machine print, you may see it come completely outside of the object and be dimensioned there as well. Okay, it can be dimensioned as 1/2 inch diameter, 1/4 inch diameter, showing distance this way, or it just might reference it in whole. Sometimes you will also see this if the leader is coming off, and it may tell you something as 1/4 inch bolt hole, or number, the quantity is 3. All bolt holes will be then 1/4 inch. It doesn't specify differences. Okay. The radius on it, sorry, let me back up. And it might tell you all are typical, all 4 places are going to be 1/4 inch diameter, 1/2 inch, 1, whatever they might be. Okay? You may not see each individual bolt hole be the same, but you might see one give you the reference dimension for all 4, or how many other bolt holes that might be in that drawing or on that project. Okay? Same as radius. It might tell you, it might give you a radius and say that all radiuses, all 4 corners, or 6 corners, whatever, are at this radius, okay? So real quick, let's talk about radius. Let's break it down. With this, what is the difference in relationship between the radius and the diameter? Okay, really quick, really simple, easiest way to remember it. Your diameter is the entire distance outside to outside of a circular object. Your radius is half of that distance. So in this case, we've got a 1 inch diameter. Your radius is 1/2 inch. Okay? So right here we have an 1 1/8 radius. Now let's multiply that times 2. Now we know we have 1 1/8 times 2. The 1/8 inch multiplied by 2 is going to be, we take the 1/8, cut it in half, so it's a 1/4 inch. 1/8 and an 1/8 combined is 2/8, therefore reduces down to 1/4 inch. And the 1 times 2 is 2. Okay? So we could achieve this 1.1 radius by cutting it with a 2 1/4 inch hole saw, or a cutter, or a drill bit. Okay? Now usually you're not going to see a 2 1/4 inch drill bit, but however, let's look right here. We've got a 1/4 inch radius, but we know if we put a 1/2 inch diameter circle in here, then it needs to match that 1/4 inch radius. So if this were an internal cut that we needed to make, we could easily center in here, take a 1/2 inch drill bit, since it's the outside diameter, and the radius of it is half of that, 1/4 inch, drill that hole, and that would give us that 1/4 inch radius. Okay? Angular dimensions, measured in degrees. So each degree is 1/360th of a circle. So to divide it into smaller units, which are minutes, which is 1/60th of a degree, divided into smaller units again are seconds, 1/60th of a minute. Real quick, the degrees are a small circle. Minutes are a single apostrophe. Seconds are a double apostrophe. So let's look at degrees real quick. So what it's telling you here is that this is a 30-degree bevel. Okay, 30 degrees. This is a 45-degree bevel on one piece only. The other one is 90. This is 45 degrees on this piece only. This is a 1/2 by 30-degree chamfer. Okay. The difference between this, we'll get into this here in a few. 45 degrees, same thing. One way you can tell pretty close is that this is roughly, if you were to build a square here, it is roughly from point to point. 45 degrees is point to point of an exact dimension square. So, let's say this is 1/2 inch. Our set and our run are the complete opposite, are the same dimension. The set and the run, when we get into trigonometry, we can also refer to those as the opposite and the adjacent. Okay? So in this case, we want to make a 90-degree right triangle out of this. Okay? So say we start here, our 90-degree symbol would be here, showing that this is 90 degrees from here to here. We are cutting it, so at this point we know that this measurement from here to here is 1/2 inch, and this measurement from here to here is 1/2 inch. Now later on we'll get into how we make the measurement and multiplication to figure out the hypotenuse, or in pipe fitting we call it the travel. There's a multiplication factor in 45 that I just happen to know off the top of my head. You take this, so if it is 1/2, or say it's 1 inch now, to keep the numbers simple, you multiply it times 1.4142. So if this is a 1 inch piece of material, I know that this is 1 inch, this measurement should be 1.4142. And I could physically measure it to make sure I am at a true 45-degree angle. Okay? I want to talk about this for a minute. Okay? See if I can find in a book where it might be. So, let's talk about degrees, minutes, and seconds. Grab my marker here. I'm going to give you one out of the book. Let's real quick say we have 22 degrees, 30 minutes, 30 seconds. Okay? So let's put this in a number that we can actually understand. Say we're just looking at degrees. Sometimes the minutes and seconds can be rather confusing. So let's just look at this as a whole number, and a lot of times that helps us understand this. So that is 22, okay? Now our minutes were split into 60, so let's go 22.5, a half degree. That's all it is. 30 minutes is a half degree. Now from there, 30 seconds is also half. 22.55 degrees. Okay? All right. Sometimes putting it into a whole number helps justify what we are doing. Okay, I'm trying to find a portion in here to move forward. I'm going to take a break and stop there.